Thanks so much, everyone, for joining us. Today we have Cam Allen. Cam is a postdoctoral fellow at the Center for Human Compatible AI at the University of California, Berkeley. His research centers on problem formalism. He likes to think about what are the right conceptual models to express the problems we're trying to solve, and how can we build agents that help us model and solve these problems. More generally, Cam is interested in the foundations of intelligence, the computations that enable agency, learning, planning, abstraction, and interaction. He completed his PhD in computer science at Brown University in 2023, where he studied structured abstractions for general purpose decision making, and he co-taught Berkeley's Intro to AI course in spring of 2024. And we're really excited to have Cam join us. He'll be speaking, I think, about a few papers, but the broad topic is the agent must choose the problem model. And it'll be about, I guess, at least one of the papers will be about an agent that can detect when its observations are incomplete and learn a memory function to compensate in this case. So yeah, we're really excited to have you, Cam. I'll hand over to you.
Thanks. I'm not sure if I haven't used Teams in a while, so I'm not sure if the layout thing is something that I can customize or if that's something that everyone gets to customize.
You mean like what you see on the screen?
Yeah. Do you see like side by side?
I see like you up top, and then I see like your screen. There is a view in the top right, and then you can change between gallery, speaker, together mode.
Okay.
I'm not sure
so
if there's a better one.
People can do whatever they like. Okay,
Yeah.
Cool. Yeah. So I guess I think a lot about this question of like, where do problems come from? I'm someone who was really interested in problem solving my whole life. I went and became an engineer for a while. I solved problems there, and then I went back to school and learned to solve different problems. And this whole time I was wondering, like, where do these problems come from? And one of the reasons that I got into AI is I thought, wouldn't it be cool if you could solve a problem that the output of which could solve another problem? And I think that that's like a really intriguing and kind of crazy idea that we've been working on for many, many decades at this point. But one thing that's kind of missing from that picture is like, where do those problems come from that you're going to send to this nice program that you've concocted, and like, and how do you make sure that the system that you've designed can actually is capable of posing its own problems? And so that's a question that I would like to try to answer for you today. So I'll try to convince you that we've made a little bit of progress in this direction, and I think this is just like early stages at this point. But yeah, let's dive in. So the main paper that I'm going to be presenting is this mitigating partial observability in sequential decision processes via the Lambda discrepancy paper. This is from NeurIPS last fall, and it's joint with all of these wonderful people. There will be some other papers that I sort of reference along the way, which will include adding these people to the mix. And so, yeah, this is a big group effort, and many separate different projects have been sort of like cooking, and some of them are still cooking. So if there's time permitting at the end, I'll try and share some of the new developments with you all. Okay, so I'll begin with a slide that I think everyone has seen before. This is the classic agent and environment slide. Of course, you always have to have one of these slides. This is what it means to solve problems. As we have an agent, it's interacting with an environment. It gets observations and rewards from the environment, and then it chooses what actions to take, and then this whole loop continues in a glorious circle. So what is this? What do people think that this is?
Are you pointing at something specific, or
no? Just the whole slide. Yeah. What is this? What is the type signature of what I've drawn here?
I guess, like, I don't know, like MDP or RL
yeah,
flow.
It could be an MDP. It might be something else. I don't know. I would start by saying that this is describing an interface, right? This is like the boundary between agent and environment defines an interface. But you could also say that this is a framework, right? This is a decision-making framework, or indeed it could actually just be a frame. This is one way of looking at a problem. You could argue that it's a cartoon. Some people would call this reinforcement learning, and then you would say, yeah, okay, if it's reinforcement learning, I know what to do. We call this an MDP, and we move on with our day, right? But I guess my point is that this is a conceptual model, and this MDP, if we're going to go ahead and define it as an MDP, we could look at all the pieces of that model. But I just want to say that there's multiple interpretations of what this thing actually even is. So let's take the MDP view for a moment and say, you know, we have some set of states, we have some set of actions, we have these rewards, a transition function, and so when we encounter a problem, we can try and map these different pieces onto the problem and see if it makes sense. So here's an example. This is a pendulum example. So we're going to have these MDP things, and we have to sort of go through them one by one. So we've got states first, and we could imagine trying to define a state space for this pendulum problem. Suppose that like the angle of the pendulum is the state. Okay, and then maybe 0 is at the top for some reason. And then we could define the actions, and maybe there are 3 actions here. Maybe we have torques that we can apply at the hinge. And then we could try and define a reward function. And so maybe we want this pendulum to be balanced somewhere close to the top of this, to this frame here. And then we get down to the transition function. And does anyone know what the transition function ought to be here? Good, everyone's not sure, and that's exactly right. You shouldn't be sure, because it might be the case if you're trying to predict the next state. Let's even say that you apply 0 torque. Like, what would the 0 torque case be? And I think if you try to predict the next state from this observation, you won't know what to predict, because it could be swinging in like this. It could be swinging in like that. And unless you have additional information, you don't know which state to predict. And each of these kind of is equally correct. So we actually can't define this transition function as is. You could say like, all right, well, you know, the reason you can't define the transition function is that there's some state information that's missing from your state. So why don't we add the velocity information about the angular momentum, or the angular velocity of the pendulum. And then once you've got that, you can look up the equations online, and this is what you get for the pendulum. And assuming that I've, you know, written these down correctly. But it's interesting that we said, like, okay, you had to augment this state space in order to make this actually something you could write down as an MDP, because augmenting the state space is not necessarily something that you can do, right? If you have a robot, the robot doesn't just get to go to the robot store in the middle of the task and pick up some new sensors from the robot store, right? So it may not have the information about the velocity, or may not have information about other stuff, and it might need to sort of make decisions anyway. You can't just add stuff to your state information if you don't have it. So I'll cross this out, and I'll say that we don't have this. And I'll also say, you know, in general, I'm interested in kind of the learning setting where we don't know what the rewards and the transition dynamics are. So we'll sort of gray those things out as well. And the agent has an even harder job, which is that it doesn't know the set of possible states either. And it doesn't know the actions. It just has names for the actions, A1, A2, A3, right? So this is the state of affairs in reinforcement learning. This is all you get to know up front, and you've got to figure out everything else as you go. So this is quite difficult. And I would argue that these agents still have it quite easy, because we're handing them the problem fully formed and ready to go, and all they have to do is apply the algorithm that we tell them to apply, using the neural network architecture that we tell them they should use. And this problem of where do problems come from is not something that they generally have to solve. So essentially, this is the picture that we're looking at here, right? We have an agent that's just looking at the pendulum, and it's got to come up with the right problem formalization so that it can go and solve that problem. So this is the model that we've been using, the MDP model, and I think it's a good model. People like this model. It makes this Markov assumption, which kind of makes all the math work out nicely. But of course, this isn't the most general model, and there's lots of other choices of models that we might consider, right? So there's the partially observable Markov decision process, right, where we add these observations, and then we add some sort of an observation function that maps from actual world states to observed quantities. You know, we can also think about bandits, where we get rid of the state information entirely, and there's no transition function. Or maybe there's a contextual bandit where you have some set of states and there's a probability distribution over those states, but there is no transition dynamics. We could look at like a goal conditioned MDP where the reward function is defined to be, let's say, 1 in a particular state and 0 otherwise. And all these different models are really abstractions, right? So they're problem models, different ways that we can formalize this sequential decision-making problem. And I'll go further and say that we typically take the problem model for granted. So many of you have encountered MDPs and POMDPs before, but when you have to decide which one of these things to use, you pretty much know from the beginning. You check if your observations are Markov, and then you say, okay, well, since I know the observations are Markov, I'll use an MDP. Or since I know that they're not, I'll use a POMDP. And I want to design agents that can make that choice for themselves. And the reason for that is quite simple. If I'm not capable of solving this problem on my own, I have no business telling the agent, by the way, here are the tools that you need to use to solve this problem, right? The whole point of AI is to help me solve problems I don't know how to solve. And if I have to tell the agent, by the way, here's how you solve the problem, then like we have failed. So this is the thing that I would like to try to fix. Does that make sense so far with the motivation?
Yep, sounds good.
Great. So so let's return to this picture. And I'll say that, you know, the problem model is really like a class of world models. A world model sort of exists over here in the agent's head. And the problem model is the class of possible world models that the agent might consider. The agent doesn't even need to have an internal world model, but if it did, it might be like some estimated reward function and transition function. Knowing that that's what you need to estimate is what it means to have a problem model. This is saying, like, this is the class of things that I know that the world can be expressed using. And so this world model, I have nothing against world models. World models are great. World models let you do things like solve long horizon planning tasks. And we should always try to solve long horizon planning tasks if we can. But again, this is a cartoon, right? This is not to be confused with the actual world, which this also is not. This is not the world. This is a picture of the world. And the point that I'd like to drive home here is that all of these models that we've been looking at are definitely not the world. They're all wrong. Some of them are useful. You know, they make assumptions that we know are false, but that may be helpful for getting things done. So here's the problem model on the left. Here's the world model, which is not the same thing. This is something that's inside the agent's head. And this is the world. Well, this is still the picture, but we'll say that this is the world for the rest of the talk. And I don't so much want to focus on world models for this talk. I want to focus on the gap between the problem model and the world, which hopefully we can try to measure. And if we notice that there's a gap between the problem model and the world model, we can try to minimize that gap and make the problem model more like the world. Okay, so that's what I would like to try to do. And the question is, how can we find the right problem model? Suppose that you're this agent, and we're going to do what we always do in reinforcement learning. We're going to drop you into an environment. And so your environment might have these three walls, and you might see an observation that is blue. And that will tell you that this is your first observation, it's blue. And so you're going to start taking actions in the environment, and you're going to see a couple of more observations. These ones will be gray with two walls. Eventually you'll get to a purple observation, and then if you go up, you'll see this yellow observation. You get a reward. Okay, that's the end of the episode. Now we'll begin our second episode. This one will start with a red observation, again with three walls. Let's suppose that the agent just takes the same sequence of actions again. So it will see more of these gray observations. Eventually it will get to this purple observation, and this time it goes up and it sees this -1 reward, and it gets sad. So if you're the agent, how do you come up with the problem model? How do you decide, oh, this is a POMDP? How do you decide whether it's the case that the red or blue observations at the beginning tell you everything that you need to know about the decision at the end, versus maybe things are just kind of stochastic, right? So this is if you had the POMDP problem model, how things would sort of unfold. And it could be the case that the initial observation sort of distinguishes between the two different sub-hallways. But it could also be the case that you use an MDP problem model, in which case the world would look like this. So the agent, given that there are 5 hallway states, 4 out of those 5 hallway states will transition back to a hallway state, and the remaining hallway state will transition to the purple state. And so it could just be that these dynamics are stochastic. How do we know whether it's stochastic versus it's partially observable and even deterministic? Like, if you're the agent, how do you know that this is not necessarily the problem model? This is just a normal MDP. Okay, so I will claim that one way that we could try and figure out the difference between these things is value function estimation. So just a quick review of some different types of value function estimation. So if we use the POMDP problem model to illustrate this, just for now, we'll get to the point later where the agent can sort of choose which model it needs to use for itself. But if this is that sort of T-maze environment, we can imagine giving the agent some policy where it runs down the hall and then goes up at the end of the hallway. And then we can that will induce some behavior in the environment, and we can try to estimate the value of that policy using a couple of different methods. So one method for estimating value is to just add up the returns that you've seen and average them together for each of the observations. So this is called Monte Carlo estimation. And that will give you this value function. You can just take my word for it. And then another way that you can estimate value is with temporal difference learning, or bootstrapping, where you take your estimate for the sort of the next state, and you kind of feed that back into your bootstrapped estimate of the value of the current state. And so you can go through the whole thing, and I won't go through all the details of the math, but this is the value function that you get. This is the fixed point of the Bellman equation. And what you'll probably notice is that these two value functions disagree. Oh no, they disagree. What happened? Like, did something go wrong? No, nothing went wrong. This is a common occurrence when there's partial observability. When you have an MDP, these two things will converge to the same value function, but when you have a POMDP, they may not. So this is amazing. Like we now have some signal that two things that would normally be identical in an MDP are not identical. And so this is like, now we have a signal. These two value function learning methods are actually members of a broader class of TD Lambda value functions, where we can look at various n-step returns and then average them together according to this Lambda parameter. The specifics of this are not super important, but what is essentially going on under the hood is that we have this POMDP. We can either solve it using the sort of like underlying states to get a state value function. Let's ignore for the moment like how we would actually do this. In practice, you can't do this because you don't know what the states are. But suppose that we could do this. We would get this state value function. And then if you do a projection into the observation space, you get a certain, you essentially get the Monte Carlo value function. That is equivalent to what you're computing when you just do this estimating, averaging over the different observations. Another way that you could solve this is to do the observation projection step first, and this will give you what we like to call an effective MDP. And this is the same picture that I showed you before. This is the one where it's like, oh, everything's just stochastic, and I assume that the observations are really states. If you were to solve this MDP, you would get some state value function that looks like this, and then the observation projection step wouldn't do anything because you're already treating the observations as states. And so this would be the value function that you get. So this is equivalent to the TD solution. So when you're computing the value function with TD, that's what's happening. And when you're computing it with MC, you're sort of looking at the original technique. And the difference between these two things, you can interpolate between these two, essentially between these two problem models with TD Lambda. And then you can like control for how much of this you'd like to do. Okay, does that make sense so far? I can pause there for questions if folks have any questions.
There's a question. Someone says, when calculating the value function, you're making a strong assumption about the alleged Markov property of the environment's transition function.
Yeah, that's absolutely right. I will say that when you're estimating it with a Monte Carlo method, you aren't making that strong of an assumption. I mean, you're still sort of aggregating everything into a single observation, so you could argue whether or not that constitutes a Markov assumption, but certainly inside the Bellman equation, there's a stronger Markov assumption. This is saying that all I need to estimate the value of the current state is the reward plus the next state reward. That means that the next state is a sufficient statistic for predicting value. And all of the assumptions that like we can even express the optimal policy as a sort of Markov function of the state, like all that stuff, yeah, those are all Markov assumptions that are kind of baked in.
Okay.
Does that answer the question? Yeah, okay, great.
Okay, yeah, they said I see, thank you. I guess I'll ask like maybe a naive follow-up question is, I guess, like why not just say, okay, I'm only using Monte Carlo estimators from now on. I guess most methods do some form of bootstrapping. I'm not sure if you'll get to that, but I guess that's like a follow-up question.
Yeah, so what you'll often find is that if you just do Monte Carlo estimation, you'll find that it has quite high variance, and so you're sort of better off with like a TD lambda style method where lambda is close to 1 but not exactly 1, and so we ended up looking at some various values of TD lambda in that project. Yeah, so this is, I mean, mostly I'll be talking about TD and MC, but you could imagine thinking about this for two different values of TD lambda, which would make stronger or weaker amounts of Markov assumption as well. Okay, so let me keep going. So these value discrepancies, we called them the lambda discrepancy in the first paper, but they reveal partial observability. You can basically subtract one value function from the other and take a norm, and this gives you this lambda metric. So this is like our little measurement tool that's going to tell us whether or not we're in a POMDP. And we have some theorems. The first theorem is that if you have a POMDP and some policy in that POMDP has a lambda discrepancy, almost all policies have a lambda discrepancy. So that means that these things are pretty easy to find. And then theorem 2 says that if the POMDP has Markov observations, then the lambda discrepancy is guaranteed to be 0 for all policies, which is really nice. So together, the two of these things say that you can reliably detect partial observability. So this is great. now let me give you the roadmap for fixing your broken problem model. So if you're the agent and you're sort of in that pendulum environment from before, or you're in the T maze and all you can see is your current observation, how do you fix the broken MDP problem model that's in your head? How do you make sure that that is actually correct? How do you restore the Markov property? Okay, step one, detect that your observations are non-Markovian. Step two, augment your observations with memory. Memory may not do anything useful to begin with, but that's step three. You're going to train your memory to restore the Markov property. And then once you've done that, you'll have augmented observations that will be sort of like observations cross memory states. And then once you have those, you can train your policy as usual on the result. So what do I mean by memory augmented observations? That's like you have this little summary of your history in your head. And one way to think about it that I quite like, and this actually ended up becoming sort of its own separate paper, is that memory is really history abstraction, right? So if there's a bunch of possible histories that take you from the blue state to the purple state, this memory is going to summarize all of them so that you can abstract away the details of how you got to the purple state and just know that you started in the blue one. And similarly for the red sub environment. So the memory function is just abstracting over your entire history, your whole trajectory up to that time. And the hope is that doing so is not going to throw away anything important. Okay, so how do we do this? So the classic reinforcement learning algorithm at this point seems to be proximal policy optimization. And so you can apply PPO with a neural network, and you can try and solve your problem. But if you ask any practitioner, they're going to say, but this might be partially observable, so we probably should just add some memory, right? So we'll do that in the form of a recurrent neural network. Okay, and now we can just turn the crank, maximize return, and hope for the best. Now, I will argue that that is not the best that we can actually do, and hoping for the best is not necessarily the same as actually getting the best. So what I would suggest is, now that we know that the Lambda discrepancy can detect partial observability, let's add a second value function head that's going to do, instead of TD, it's going to do MC, or instead of TD with some Lambda, it's going to do it with a different Lambda. And then we're going to take the discrepancy between these two things, this Lambda discrepancy, and we're going to minimize it. So we're going to minimize it as an auxiliary objective alongside the traditional reinforcement learning objectives. Okay, and so we tried that. We tried it on this really hard Pac-Man environment, which is partially observable. The agent sees the stuff on the left side. Imagine that you're trying to play Pac-Man, and really what's going on is on the right, but you're playing as if all you see is on the left. And if you've ever tried this, you'll know exactly how hard it is. It's quite difficult. Here's how well a recurrent neural network does on this. So after 10 million time steps, we're starting to get a score of like maybe 1,500. I don't know what's going on with this learning curve here. It seems like maybe PPO is not even that stable on this problem. Like it gets to some, I don't know if you guys can see my mouse, but it gets to some value and then it kind of drops after that. Now we added this auxiliary objective and we minimized the Lambda discrepancy on top of the PPO objective. And we got this learning curve, which I'll just illustrate for you in terms of episode performance. So we'll speed the one on the right up because it does sort of too well to fit into this talk. So the difference between these two agents is kind of night and day. And we were wondering, like, why is the green agent so much better than the blue agent? Why is minimizing Lambda discrepancy helping? Is it learning a useful memory function? And the nice thing about Pac-Man is that you can actually visualize what the agent remembers by trying to reconstruct the status of the dots in the grid. So the dots tell you where you've been. And if the agent can, from its recurrent neural network hidden state, if it can reconstruct the locations of the dots, then it will sort of tell you, it'll indicate that it knows where it's been. So I'll show you what this looks like. On the left, we have the we have the reconstruction from the base RNN. And on the right, we have the reconstruction of those dots from the Lambda discrepancy minimizing model. And so you can see that, like, on the left, the agent kind of has no idea where it's been. This thing is flashing all over the place, and like, it sometimes knows where it is and sometimes it can't tell. And then on the right, it basically perfectly tracks the red line. It knows exactly where the agent's been. Okay.
Just a quick question on the
Yeah,
problem.
please.
That's okay. Is a starting state like distributions, like, do you always start in the same place, or?
In this environment, you always start in the same place. Yeah.
Okay, and like the goal points, are they randomly shuffled each episode, or the food things?
No, I think this one is deterministic.
Okay.
There might be slightly different randomness in the simulator, but I can't actually remember whether the ghosts do the same thing every time or different things every time.
Okay. Okay.
Yeah. Yeah, so it's interesting because, yeah, basically the fact that you know where you start means that you don't have to do localization, right? You're already localized, so all you have to do is you do sort of like mapping during learning, and then you just need to come up with some memory function that can tell you, what you already know about your environment. Okay.
Oh, makes sense.
Okay. So before I said, we have this problem model on the left. It's not the same thing as the world, and the problem model that we said was a POMDP, but we wanted to use an algorithm that's like an MDP algorithm, and we wanted to hopefully make it so that our observations are Markov, and we had the confounding problem of not knowing what the actual states were, not knowing the reward function or the transition function or the observation function. So this is where we were operating. And what we found was that by adding this idea of a memory function, we could come up with a better problem model. And that, hopefully we could, solve our problem more easily. Okay, so what's next? What's there left to do at this point? Have we solved the problem? Well, I would say no, this is just the first step. So one question you might ask is, what if there are no rewards? We've been using value functions this whole time. If there's no rewards, there's no value functions. And then, are we just completely screwed? And this can especially come up if you have an AI assistant that cannot fully observe the human's reward function. And all it gets to see are the actions that the human's taking. So somewhere inside the human's head is a reward function that we don't know what it is. We can actually model an assistance problem as a POMDP, and then we can try and apply this same sort of approach. But if we never see the rewards, then kind of there's nothing we can do. I think, we might also say, like, these are two problem models. We have MDP and POMDP. But what about, other problem models? What if we want to decide between even more problem models? What about, like, classical planning? What about bandits? What about, classification? Are any of those reasonable problem models to consider? And are there new problem models that nobody's invented yet that might be worth thinking about too? Like, where would those come from? And can the agent start to build those for itself? In the time that's remaining, I will focus on this question here. So what if there are no rewards? And we'll sort of dive in. So earlier I showed you this slide. I said value discrepancies reveal partial observability. And I said if some policy has a Lambda discrepancy, almost all policies have a Lambda discrepancy. So if some policy has a Lambda discrepancy, well, what if no policy has a Lambda discrepancy, but it's partially observable anyway? Then how would we handle that case? And in fact, when I say value discrepancies reveal partial observability, I really should say, like, they usually reveal partial observability. So here's an example that we quite like. And we had a version of this called the parity check environment in the original paper, and then my intern this summer, Peter, sort of simplified that even further, and I think came up with this even clearer description. Imagine that we have an environment where there are 3 coin flips, C1, C2, and C3. C1 and C2 are independent, and they're both sort of fair coins. C3 is always the XOR of the first two flips. Okay. Hopefully I've done that correctly. It looks like I have. Okay, good. So if you do the math on this one, you can apply. Let's suppose that you ask the agent to predict C3 on the second time step. You could get to the situation where you have like a reward function for this environment. If you don't do that, you don't have any reward function. It kind of doesn't matter what the reward function is because the lambda discrepancy turns out to be 0 for all reward functions in this environment. So it doesn't even matter like if you have a good reward function or a bad reward function, like you're never going to be able to detect that this is partially observable, that you need to have some amount of history for this environment if all you're doing is looking at lambda discrepancy. So this is kind of like the failure mode. And the question is, can we do anything about this? And I will tell you in a second that we can do something about this. But let's first rewrite this lambda discrepancy in the following way. Okay, so we have this difference between value functions, and then we take the norm. And a value function is really just an expectation. And I'm writing the expectation as this P bracket notation. So that's the notation in the bottom right. It's just saying like the expectation where some argument of a function is drawn from that distribution, and the distribution is either the Monte Carlo distribution or the TD distribution. So this is like we're either drawing observations from the PUMDP or from the effective MDP. And then this capital F function is the return, which is just summing up for some horizon the gamma discounted rewards. So the question is, can we replace this F? How general can F be if it's mapping from histories of observations to real numbers? How general can that function be so that we can still estimate these two quantities? Now, it's pretty easy to estimate this Monte Carlo quantity because we can always just take a bunch of samples and then take the average. But the big question is, how do you do this TD thing? TD requires this bootstrapping update. And so there's a limited set of functions that actually can be written down using a bootstrapped estimate. But one thing that we can do is we can replace the reward with some other observable that's a function of the observation. So if we have some other observable little f that maps from observations to real numbers, then we can of course take discounted sums of that, whatever it is, and we'll still be able to do this. And this is called a general value function, or sometimes it's called like a successor representation. And the discrepancy that is formed when you do this is the discrepancy between successor features of the PUMDP and the effective MDP. Let me pause there and see if that makes sense to everybody.
Yeah, I think it makes sense to me. I'm not sure if
Okay.
anyone's...
Okay, great. So let me sort of make some room here. The question here is, how general can this function be so that we can still estimate it using estimate it for the Monte Carlo version and the TD version. And the TD version, it should hopefully be clear that in order to do that, we're going to need some sort of a recursive estimate, something we can write down a Bellman equation for. So we want the functional form of capital F to be some recursive function that takes F as an input, but at the next observation, right? So we want to be able to write down F in this way, in this recursive way. And then the question is, what can H be? Okay, so if we write down the value according to the effective TD model of this F function, we can write it down as the expectation of F applied to that whole observation stream. And ideally, we want this thing to be recursively estimatable using a Bellman equation, where the inside of that equation is the expectation at the next observation. So that's really the goal here, some sort of a recursive update for this value function. And so what is the functional form of H? What is sort of the most general version of H in order for us to get this sort of expectation, recursive function and expectation setup? Well, what we need is we need this function H to be linear in F. Otherwise, we can't move things inside and out of the expectation. So we need it to be linear. So that means we have some intercept to play with and some slope to play with. And these can be functions of omega, but F is sort of restricted. So we get this F of omega and this gamma of omega, and this is sort of hinting at the functional form that this is eventually going to take. This is the Bellman. We can do this, and we get a Bellman equation for TD learning of sort of an arbitrary function, capital F, and the green lowercase f is the same as the orange one up here. This is just some observable of, some function of our observations. And then this gamma is now saying that we're going to do discounting in an observation-dependent way. Okay, and so what that sort of putting all that together, what that looks like is that we have this function f, capital F, which is sort of essentially the generalized successor features that we're trying to basically multiply all of the gammas for all the different observations along the path together. And then we're summing these things up as t goes from 0 to the horizon. So we take our pseudo rewards, we multiply them by our pseudo discounts for all of the time steps this far, and we can estimate this using this recursive Bellman equation style update, which is really great. Okay.
Cool. Just a question.
Sure.
We are maximizing this pseudo reward f function in this case. Or like what are we
really
trying?
we're not maximizing okay, if there were rewards, we would want to maximize the discounted sum of those rewards.
Mm-hmm.
But these aren't really rewards. These are just observable things in the environment. So what we want is to get an accurate value estimate. This is like a general value function estimation problem. So this is really just like value function estimation. You want to say like, what are the value functions for my policy under these different sort of observable quantities?
Okay, and what are the value functions estimating? Like what
would so this could be like the expected number of discounted times that you saw an observation. Okay. And then you would have like a proper successor representation. Or you could do some kind of like encoding or embedding of that observation into some other space, and then it would be a successor feature rather than a successor representation.
Okay, cool. Makes sense. Thanks.
And those two things would be for sort of a fixed gamma, but now we're going to let gamma vary as well, and then we're going to get this nice coupling between different time steps. And that coupling is going to be what it takes to solve the parity issue that we saw before. Okay, so again, I'll make some more space, and I'll just say that this thing is called the generalized value discrepancy, and it's essentially the difference between these two capital F functions for some gamma and some lowercase f. If we go back to the coin example, we saw that lambda discrepancy was 0 for all reward functions, but it turns out that the generalized value discrepancy can be non-zero here. And we have this nice theorem that says that this generalized value discrepancy will be 0 for all f's and all gammas, these observation-dependent gammas, if and only if the POMDP is actually the same thing as the effective MDP. So if these things produce the same sequences of observations, then there is no difference, and you'll never be able to detect. But as long as they are different, then there exists some f and gamma that will detect the partial observability. So essentially, if we go back to the original thing that I had before, now it's the case that the generalized value discrepancy can always reveal partial observability, and so this is a theoretically perfect signal for detecting partial observability. We ran this proof of concept experiment, and just confirmed. So basically what's going on here is we have the relative performance of the different methods, where a memoryless policy is in gray. You can ignore the pink and red. I'll come back to those in a second. Lambda discrepancy with different amounts of memory in blue, and then generalized value discrepancy in yellow and orange with different amounts of memory. And so what we see is for the environments that lambda discrepancy did well, generalized value discrepancy still does well. And for the environments where lambda discrepancy did poorly, notably T-maze and the parity check example, the two from this talk, generalized value discrepancy does quite well. And in fact, it solves the parity problem. The red and the pink lines are just sort of baselines. If you had a memory function that was randomly initialized of a certain size, that was not trained by any sort of like discrepancy minimization. Okay, so it improves on T-maze and it solves the parity problem completely. So now I'll sort of recap the various contributions. So we have value discrepancies. We introduced value discrepancies. Value discrepancies detect non-Markovian observations. They facilitate learning memory functions. They mitigate partial observability, regardless of reward. And they allow the agent to automatically correct its problem model when it's found to be incorrect. So that's the key piece here, is that the agent comes into this not knowing the set of states, not knowing the rewards, not knowing the transition function, not knowing the observation function, and not knowing whether the POMDP model or the MDP model is a more appropriate problem model for the task. We would like to use all the nice sort of Bellman equation math that MDPs allow us to use, but we don't know if that's a good thing to do because we haven't encountered this problem before. And now we let the agent figure out for itself which of these things is more appropriate. So I'll leave the QR code there. I think I already shared it in the chat. And I'm so happy that I was able to hopefully convince you that the agents choosing the problem model is the right thing to do, and that's what we should be doing.
Cool, thank you so much. Yeah, this is excellent presentation. I think I'll just find the clapping emoji. Cool, thank you so much. I think there were some questions in the chat, and I also have some other questions. But for now, I'll just stop the recording, and then we can ask those questions off the recording.
Sounds great.
Cool, thanks again.